Start streaming. All right, cool. Welcome back. Congrats. We're back on top. UConn Women Championship. Woo. That was pretty awesome. For Module 3, we're wrapping up. We have Project and Quiz 3. Quiz 3 I'll get online after classes today, so by this afternoon that'll be up there. I can push off due date by a day or two. Like, I think it's due tomorrow, but let's push it off so that there's actual time to carve out and do the quiz. I think that'll work out better. And then usually what I like to do is start off with the pendulum experiment, like hang a pendulum out like a third floor window and try to measure something about it, like look at the measuring. But today it's raining, so I don't want everybody standing outside in the rain watching a pendulum slowly rock back and forth. So we'll do that next time, Wednesday. Wednesday looks like clear weather, so we'll do pendulum experiments next time. Today we'll do predictions of like what can we actually predict and then try to measure for next time. Sound good? That's the plan. So next time, bring your safety goggles. All right, there are two different, so we're gonna look, this project is like comparing two different ways of getting to a solution. Same thing that we did for that like block on an inclined plane. Like we created an equation of motion and then we solved for it. So we have some degree of freedom that we chose. For a pendulum, the angle kind of makes sense because if we know the angle, we know where it is. We can calculate its XY position. So there's two different ways of talking about a pendulum. A linear pendulum differential equation and then the full kind of non-linear one, but we have to integrate it numerically. What do we know where these two came from? Like if you have these, one of these or both of these equations, what does your free body diagram look like? Like what is this actually describing for a pendulum? Or what does the pendulum look like? Like where is theta? What is L? What are these things? Yeah.
I think theta is the angle between like the horizontal axis.
Okay.
Vertical
one.
Axis, vertical axis and the string.
Yeah.
At any time.
So we draw a vertical line, and then there's like some kind of string going off at an angle, and that's theta. Something like this.
Yeah, I like this string here. Is your L.
And then that's L. Okay. Any like constraints on motion, or because we only have one differential equation. So we're only describing one degree of freedom. What's happening to the other one? Does that question make sense? If we have, so if we're trying to describe like a point in space that has 2 degrees of freedom, but we only have one differential equation. So somehow we went from this thing can move x and y to this thing only needs one free motion. Yeah.
We were describing it with R and theta, but we said that R was fixed when we labeled it.
Okay, so R is fixed here. So like R is always equal to L, and like its position is some kind of like oh, that should be R. Kind of like this R is always ER. So what does that look like for like a engineering diagram? What's happening there? Or like reverse engineering this. We're going from the differential equation back to a diagram. What do you think? Can you sketch it out? Try it out. Shouldn't take too long, right? We don't need like great artistic skills. We don't need any Martians or anything, or moon people. I guess it was the moon rover, right? Lunar rover. What does it look like? Yeah, you can do free body diagram. Yeah.
So I guess what I'm trying to do is like figure out.
G pointing down.
Right. So like, when is it 0? I guess is what I'm saying. When is sine theta 0?
At 0.
Yeah. So that would be
like
so
reverse.
that means that the acceleration is 0.
Okay. You think there's this different force for the nonlinear one?
Because
Oh yeah. Acceleration is 0 there. So we're looking at acceleration.
Okay. Yeah.
Yeah.
Okay. Yeah, sine would be positive to negative. Similar to theta. Theta is positive to negative. So either like a free body, we either want to know like what is a free body diagram or what is like the engineering diagram. So where like is it constrained, where's our mass?
Oh, I wrote it down.
For at least like for this pendulum, you know that's a differential equation. Makes sense to me.
yeah. I only have 3
Okay.
No, I have 4, but when I was doing this
Along that straight. Okay. So it's we think there's another force. Is that part of our differential equation?
Oh, I remember.
No.
We should like
No.
Oh yeah, that's
yeah.
Okay. Yeah. We're trying to figure out like based on those equations, what does a pendulum look like? Because we're kind of doing the we've been
It is a good exam to make
What is
it.
mine?
And then I have an Italian cinema exam that's the previous week, but like during the class time.
Mine's the same as yours, except I have. You don't have to.
I don't have to. Well, I got my, no, because I got the project. And he said that's due like really early in the week. So he has time to grade everything. I don't think so. It's scheduled, but. Oh, never mind. Yeah, 6 to 8 p.m. is kind of crap. They don't want to know that.
Oh, DTQ and Sigma are the same.
Is that something you want to get into?
I'm a professional gambler. Who do you think you're talking to? It's like a public plus it's like ripping off the after that, it's all like, oh,
Nice. So I'm gonna have to move out until classes and yeah, that's previous week. And the weekends, no homework.
Yeah.
Well, no, the point is we're supposed to study during those days.
you think everything. That's how I do it. It works out. Like, look at Google drawing. What are we actually describing that?
Both, I mean, both of them.
Oh, wait, you can just do this.
Slightly different.
Oh.
Yeah, no, he's an engineering diagram.
Oh, I have paint, so let's go.
MS Paint?
Yeah, why didn't you use it?
I don't know, I just Googled draw, and this is the first thing that came up.
It's a circuit diagram.
Yeah, for
Oh, circuits are getting shit. Like really?
what?
What I'm hearing the professors like actually.
Oh yeah, look until my scale.
Oh. I've been hearing from some people that
Who are some people?
literally other honors kids.
Oh, you say, well, you don't trust me? About the games there?
Yeah.
Oh, is there a straight line tool or there is?
I just draw a messy line. Oh, I can put like, it's asking if I need to draw a soccer ball, I need to draw. I think I can't tell if I'm missing.
So I saw kind of like we said like R is L, and so our origin is a fixed point, right? So in this case we could draw it like a hinge, something like that. It could be, yeah, I'm trying to think if there would be anything else. Usually like hinge, right? That'd be the main like engineering, some kind of hinge support. And then where was our mass? Right at the very end of it, right? And now which way is gravity pointing? Straight down?
And you can kind of like help when I do that. You look at it like, we're looking at acceleration in theta double dot. If you look at the non-linear one,
Yeah.
G L sine theta, when it's directly vertical, that value is 0 because gravity's not like actually moving it down. It's because R is constant.
Yeah. Yeah, so R.
Yes, gravity's still acting on it, but at that point gravity's not moving it in the theta direction.
Yeah, at least like acceleration when theta is 0, there's no acceleration. Like acceleration's always some function of how far away from 0 we are, based on, and again, like based on how this diagram is kind of working out. So with this differential equation, we were kind of, some thoughts came up of like, oh, is there initial force to like get it to move? Or maybe is there friction? Is there damping? Like, are any of those things included in this differential equation? No? Why not?
And if you were to graph it, it would go on in a sine wave forever.
Sine wave forever. So some kind of, it's like harmonic motion, right?
G over L is a constant. So
G over L is constant.
Constant sine theta, and you graph it. You just keep going.
Okay.
If there was a damper, they'd be trying to make it diminish over time.
Yeah, so yeah, nice. So if you're looking at a differential, at an equation of motion, and you see something times v, like some kind of d theta dt or dx dt, like something where there's a term times its speed, some measure of its speed, that's damping. It's taking energy out of your system, so it'll decrease its amplitude over time. But if it's not there, then it's always going to be some kind of harmonic. Even in this nonlinear case, we're still going to have like a harmonic motion because it's always a function of theta. Kind of makes roughly. I'm glad I asked. This was. So we only have that tension and gravity, right? For our free body diagram. Tension is always like perpendicular to our motion, so it's never actually accelerating our object. I mean, it is causing acceleration, right? Like there's centripetal acceleration due to tension, but it's not changing its speed, I guess, is the main thing. It'll change its direction, but not its speed. That's what I was trying to say. All right. So when we have like sine theta and theta, what's the difference there?
It's the linear approximation. It's more accurate.
Linear?
It's most accurate for small values.
Okay. How small is small enough?
I think we said like 30 degrees or
30? 30-ish, maybe? Ballpark? You're like 15?
Yeah.
Everybody's going to have a different number. If you're like a hardcore physicist,
Physicists are like 10,
then
15 degrees.
it might be like 0.001 radians, and then you start introducing non-zero errors. But engineer, it's like, it's fine, guys. Well, let's test it out. We can launch out some. We'll go into project number 3. I'm going to run through some stuff. So at least right now, oh, not that one. To start, I'm just going to say like initial angle is 60 degrees. So first number that we threw out there was 30 degrees. Let's double it. See how good it is. Anyway, for that linear solution, do we have it written out? Yeah. So it's written out. It's catching up. For that linear differential equation, this is the solution. Like it's just. And we can derive it, like you can use differential equations to get there, or you can always say like, I have a second order differential equation, only position in there, and this is gonna be your answer. Initial angle times the cosine term, and then initial speed times that sine term, which kind of makes sense because like cosine has a 0 slope, so it's gonna tell you how big your initial angle is. Sine has a non-zero slope, but it starts at 0, so it's telling you initial speed. So some combination of those two. And that's always the linear solution. So we'll run that. And so far, here's like 2 time periods of a sine wave. Starts at 60, swings down to -60, back to 60, and back, just harmonic motion, just like we thought it would be. And we kind of programmed it in there. Have you seen like a nonlinear integration, like what to do with differential equations with a computer, like how to tell it, just, hey, solve this for me? This is it, this is the time. This is like, you get the sword from It's Dangerous to Go Alone. Take this numerical integration scheme. All right, what we need for a computer, whenever we want to tell the computer, like, hey, solve this problem for me, like I have a differential equation, I just want to know what happens next. We need to take that nonlinear differential, like second order differential equation, turn it into 2 first order ones. Because it's easy to solve a first order differential equation, it's hard to solve a second order. I don't make the rules, it's just, that's how it goes. So the first equation that we have is that, we create 2 variables, theta and then theta dot. So then our differential equations are going to be derivative of theta and derivative of theta dot. First one, d theta dt is theta dot. Second one is d theta dot dt. That's our differential equation. That's negative g over L sine of theta. And that's x0 and x1. We don't have to worry about it too much, like, but I did want to at least give you a look under the hood of like what's happening. It's going to just give us a solution. So with that function, once I have a function, I can give it to this thing called the initial value problem solver, and it's going to give me answers. But it's not giving me a function of time, it's literally just giving me like a whole bunch of numbers. Like this is angle and theta dot at time, whatever, 1.3 seconds. So we don't get functions, but we get lots of numbers. Again, great for engineering, not so great if you're like really big on accuracy and like maintaining physical principles. So already we see some, over the same time period, we were trying to plot like 2 swings, something's a little different. So if we run a comparison between the 2, what do we see that's different so far? We have blue is a linear solution, red is our nonlinear, like sine theta solution. What do you see that's different? Yeah.
The first thing stands out with the frequency, I guess the period
Okay.
of each.
Period or frequency, they should be directly, right? There should be some direct relation. Yeah, so period or frequency, those are different. Anything else? It's the main thing.
I think that's, yeah, the amplitude is the same.
Ooh, amplitude is the same, right?
Yes.
Which, I mean, that makes sense because there's no friction, no damping, so whether it's linear or nonlinear, just conservation of energy. If I had MGH here, I gotta have MGH over there. So we have to have that same amplitude even for different things. All right, so we see, rather than like, we won't keep going down, let's find a number where we think angle is small enough that small angle works. I guess that's the first question. Can we use small angle approximation here? Is it good enough? Or are you?
I think if you could use any angle you want, it could be as small as you want. But if you were to plot it out over a really long period of time, eventually you notice a difference no matter how small the angle is.
Oh, you think so?
But over That's what I'm guessing.
Oh, interesting.
Over 4 seconds, if you were to cut the angle down to like near 0, I don't think you'd be able to see the difference.
So we want to increase time or decrease? You think decreasing time would?
No, I'm saying decrease. Are we trying to change the time or angle?
I was gonna change initial angle and see where we're okay with small angle works.
Yeah, that's what I was saying. Is
Okay.
If you decrease the angle near 0, if you have it over like the same amount of time, like
Yeah.
the graph, it should get closer together. I don't
Okay.
think it'll be exact.
All right.
I'm also guessing.
I think that small time intervals, the graph would be accurate, like regardless of the.
Yeah. Yeah. So if we're just looking at a few times
Yeah,
at a
it's like
small
1 or 2
period of
seconds.
time, probably doesn't matter too much. So how small do we want to make the angle so that it's small enough?
We should rest in different values.
Yeah, we can go. We can do as many as we want.
And then just
You think 15?
Pi over 6.
Pi over 12, right? Is 15. Pi over 6 is 30. You think pi over 6? Try that one first.
Confuse myself.
6 is 30. So we'll take a look at this. And I'm just running, I'm not changing anything, I'm just doing like running it again. So now it goes 30 to negative 30. Now we have blue and red still linear, non-linear. What do we think so far?
my guess was
Pretty good? Feels good, right?
did you run all the I guess.
Yeah.
There's still like a slight difference in curvature,
Okay.
like the rates of curvature of the two graphs.
Yeah.
But they still like have sort of same points like at the bottom.
All right.
It still starts at 30, and then after 1 second, both of them are approximately at negative 30.
Yep.
The thing is, if you were to like extend the time axis,
Yeah.
you would see the same thing happen as last time. It would just take longer. But if you took, if you looked at it at 100 seconds, it'd be pretty far off.
Okay. You want to see like more time? How many time periods do you want to do?
We're doing 2.
How many factors there?
Right now we have 2 time periods. You want to look at like 10? All right. So 5 times that. Oh yeah, let's make. We'll go 1,000. Well, 1,000 time steps along 10 time periods. Oh, I'll go back up and show in a second. Is that what you're thinking? Is that it'll slowly?
Because if the frequencies are off by a little bit, the difference will become more obvious over a longer period of time.
Okay.
Yeah. Yes. I would say.
What is it? The
Like blinkers, like at some point in time, they blink at the same time for like 1 or 2 rotations.
yeah. Okay. Even if they're even if their frequencies are slightly out of phase, like at some point they'll look like they're in phase if it's close enough. Like yeah.
And then
Yeah, and then they'll start
this
going.
just goes out of phase. Actually, at some point it would come back into phase.
Yeah. Yeah, like if one time period is like 2.01 seconds and the other one is 2.011 seconds, then we're probably figuring out, yeah, after about 10 times, and we're 1/10 of a second or whatever, 100th of a second out of phase, right? So we'll come back eventually. Oh, and to answer, if you're trying to do that experiment, this was where I was changing everything. Setting up time, I gave it 1,000 time steps. That's the last value. And the second value is like 4 times pi over w. That's the 2 time periods. So 2 pi over w is 1 time period. Yep.
Would 20 times ME.pi get the same thing?
20 times pi over w.
If you just got rid of the 5 and the 4 and just put 20.
Yeah, that would work. It's still the same. Yep. It's just there was already a 4 pi, so I just said if we want 10, then let's do 5 times that.
Would you change the angle?
No, I changed it to 1,000 because before I had it like default and the line was so jagged.
Yeah, if you only, so default is 50 steps, so it only gives you 50 equally spaced points along the way. All right, so pi over 6, we see that it does start to go out of phase. So do we need to go even smaller or leave it as pi over 6? It's like we're good enough for now. Good enough for government work.
I think it's good enough.
Good enough. All right, so let's go back to 2 time periods. At least on what I'm looking at, 2 time periods.
So just get rid of the 5 times.
Yeah, at least if you're trying to do same thing that I'm doing. What I want to look at is theta as a function of time, theta dot, and theta double dot. So I've got all 3 curves. Because once we have like theta as a function of t, like the solution, we can solve for whatever we want from there. We can get velocity, all sorts of stuff. And we're still, yeah, it's still 30 to negative 30.
What is the amplitude on the third one now?
Okay.
The amplitude looks different.
Why is the amplitude different?
Oh, that one there, theta t. So
Theta double dot.
That's it. Oh, I missed the double dot. So that's
Yeah. So radian per second squared now. Why is that one different?
which one is which? Blue is the.
It should be, let me double check. I should put labels on here, right? Theta. Oh no, this one's switched. All right, blue is linear.
What did you switch?
Sorry. I realized the second plot was the velocities where red and blue got switched. So I just took those 2. Plot d theta first and
Oh,
then,
you switched the order.
yeah. Because blue is always your first plot, red is your second plot. Yeah.
We changed the order. So we put one of the statements before the other.
So just so blue is the real one for the approximate.
Blue is linear.
Yeah, you just switch it.
So what do we see? What do we see that's the same or different between these plots? In this first one, we said it was kind of like close enough, at least to start. We said the engineering, this linear, non-linear, it's close enough for engineering work. How about for speed? Is it still close enough, or is something changing?
Not the smaller. Those are the smaller values again.
Okay, pretty small.
This one changes. I guess it changes at the same. No, it changes like a way at the same rate. I don't know how to explain it.
Okay.
And now it has the same amplitude. The third one does not have the same amplitude.
Third one, amplitude is different, right? Like for if I take this value to this. So that nonlinear amplitude is not the linear amplitude, but just an acceleration. Why is that?
The linear amplitude is greater.
We have a bigger linear amplitude, right?
Yeah. Well,
Does that make sense?
I'm not sure. One thing I did think is the nonlinear one is restricted to the limits of sine and cosine, but
Yeah.
the linear one is not. So it's actually exceeding what should be possible.
Yeah, like so on a swing set, like if you're swinging on a swing set and you start getting big angles, like you always, at least like as a 6-year-old, you got to try to flip over the bars at least once. So as you get up to like 90 degrees, you don't have pi over 2 g over L swinging you back that fast. It's the sine of that, so it's like maybe up to g over L, like that's your max acceleration. And that's kind of where we're at. We're even for a small angle that we think kind of works, we're gonna notice some difference in acceleration. And if you want to do like the math version of it, that's our linear, and our nonlinear, whenever we're saying like theta equals negative g over L, sine theta versus we have like, I guess I didn't put the negative sign because it's all positive, but that's all right.
Yeah, I'm gonna have a hard time understanding how does that picture help us understand why the linear one exceeds the amplitude?
So the bigger the angle, the bigger like our delta theta double dot is the difference between g over L theta and sine times g over L theta.
Is the horizontal axis?
Oh, this would be theta, and this would be like theta double dot. If we're thinking about like what is theta as a function of, or what is theta double dot as a function of theta, since that's our differential equation. So let's try the other extreme. Like, how big is too big? When does this get like terrible?
90 degrees.
90? You think 90 is going to be the worst?
Or can't engine above 90.
You can't bring it above 90?
Definitely.
So pi over 2. Go 90 to negative 90. 90, negative 90. Now we see like a distinct difference in time period, right? Like a very measurable difference in time period. But we can't go above 90? How big could we go? 180? What's going to happen if it's 180?
No, then it just falls straight down.
Fall straight down? All right, let's try 180. All right, linear says it'll go from 180, swing down and around and back up to 180. This is a little different than like a swing set, because if you start at 180, you would fall, like we were saying, like it's a string and the string would collapse and you hit the pole, comically bounce off of the top of the swing set. But in this case, we didn't set a constraint that tension can't be negative. So really it's a rigid rod, at least in our differential equation. So it's not so much that there's a string attaching it, it's like there's a rigid thing connecting mass to this point, and it always has to be R as it moves around.
The non-linear model is not moving.
Not moving?
Like if you really had only
If
gravity
it's,
forcing it down, you had it like perfectly vertical.
Yep.
It'd be really hard to do in real life.
which is
If it was
what
perfectly vertical, it wouldn't move.
we get kind of a weird graph for nonlinear. Is this not moving, or is this moving? Part of it is that it's kind of hard to read the plot.
I don't know.
But the theta's not changing.
Well, actually,
Well,
it's no, it's
Oh,
like
eventually.
right? Because like, it's not gonna be exact. Because I'm using like NP.pi, so it won't be perfectly exact.
Yeah, there's like round off error. So pi is not exactly pi.
Is that why we're having it move? Like,
Is it moving though? I guess.
I
It's
mean,
kind-
like pretty rapidly at the end.
You think rapid?
Oh, like at the end, yeah, it jumps.
Yeah.
to the negative
degrees?
This one, I don't love like how the default is, but this axis here is telling you that it's 180 degrees plus any of these numbers times 10 to the negative 10. So like when it's 1, really it's saying it's 180 plus 1 times 10 to the negative 10. And when it's negative 1/2, now it's 5 times 10 to the negative 11.
So this is due.
We're basically looking at a round off error plot, because when we plot them together, here, it'll catch up in a second.
There it is.
It looks flat, right? Nothing's happening, which is kind of what we expected. It's like, if you're exactly 180, it's just gonna sit there. But our linear solution just says it's gonna swing back and forth. Which one's right? Which one's more right?
The linear one.
Well, if it's vertically, there's the gravity's going down, tension's going up
Yeah.
perfectly.
Yeah, so nothing's moving.
Non-linear
Non-linear is the flat.
Oh,
So the one that doesn't move, we think is like, that's the true
Yeah.
answer? Okay.
In the context is
But it's perfectly straight, which, I mean, that never happens. Yeah. It's, even when you do get it like upside down.
I guess like the
Sweet.
particular, the linear approximation is exactly that. It's just an approximation.
It's an approximation, yeah.
It's less accurate the further out you go. It's gonna be like extrapolated.
Yeah. Yeah, and if we want to look at like the extremes, let's go to like 0.95 pi, like almost 180, but just a little bit below. We'll still get a linear solution that doesn't change, at least magnitude changes, but the frequency does not. Now our nonlinear does this, where it's like slowly nothing's happening, and then all of a sudden rips through 0 degrees and then back up to almost stable. And let's look at the comparison like across everything. Yeah. And this one, so I'm doing this to show like one, like what do these linear solutions look like? So like it's always some function of like initial position and initial speed. Then also like when we have nonlinear effects, like what's happening, like what's actually nonlinear in these cases. Next time what we'll do, so this is like a mental homework assignment, like you don't have to write anything down, but we're going to measure pendulum motion. So think about like, what can we measure that's simple and accurate? Like how do you be simple and accurate for just like a pendulum swinging in a classroom, and then I'll bring it upstairs and we'll swing it out the window and we'll see. Because we need something like bigger is better, like a 3-story pendulum. That's the way to go. So we'll swing it out my office window in the back of E2. We'll measure that one. So think about what are we going to measure and how do we make it like accurate? And then how do we predict so that we have a comparison? It's our mental assignment. Cool. All right, I've been talking for a while. I'll check in, and next time we'll do the experiment, and I guess the last thing that might help is like what other calculation can you do? So we looked at all the different like state, like theta, theta dot, theta double dot. What else could we measure and compare between a linear and a nonlinear?
If you're looking at the graphs, you can measure the difference in period.
Difference in time period. So that's one way of measuring like what is the difference. So that's like
Okay.
the first step of like what is the difference between these two answers. Time period is a big one. We saw amplitude is a little different when we look at acceleration, and it depends on how big. Like in this case, we have a very big difference in amplitude for accelerations. So that would be like, how do we quantify that error in what we have? Well, what else could we calculate with this? And we can also talk about it next time too. We haven't really talked about it, but I know you've been working with like work and energy.
Oh yeah.
That would be like if we know angle, we should be able, or momentum, like if we're looking at like, we could also look at where is this thing, like what is the path this pendulum follow, like what are the X and Y variables. Yep. Or how much tension do we have? Like what does tension look like? What does tension look like for a linear solution?
Would it be constant?
It should be constant, right? Because we only had like tension. I mean, I guess there's still that theta dot squared, but if we're saying theta is small, theta dot's also small. So for a linear, T equals mg, right? But nonlinear, we have like ml theta dot squared. But next time we can take a look at like how we could plot those two and compare them. Or you can look at like mgh, 1/2 mv squared, what those would be. But somehow it's like one other thing to compare between the two. Sound good? All right, thanks.